Welcome to EC Fedu blog. I'm still your physics teacher. Now we are in the section, we are still in elasticity. We are in the section of energy stored in an elastic material. Now some textbook also calls it work done in an elastic material. We are still the same thing, it doesn't matter. Whether energy, work done means energy in physics. Okay, now let's define what work done in an elastic material means. Work done by an elastic material is the product of the average force. Average, and whenever we talk about average, it means you are dividing by 2. The product of the average force and the extension caused by the force. Now, some of you that are very smart, what you normally see in your test is this, that the work done is equal to half of the force times the extension. This is correct, but what they fail to show you is where the average force is coming from. Initially, by this is supposed to be the force applied plus the force, initial force, divided by 2 now times the extension. But we know whenever something is standing, for instance now the elastic material is standing on its own, no force is initially applied. Therefore, this becomes our initial force, which is becomes 0 divided by 2 times E. This you will not see in any of your textbook. Very important. So that's why this formula now changes to this. Now F plus 0 gives you what? F. So you now have F times E divided by 2. So this is the formula for the work done by an elastic material. But we know from Hooke's law, the force F is equal to KE. So if that is true, that means that the work done now, this is correct for work done. This also means that the work done is half. Anywhere we see F, we now put KE. K times E. This KE represents F times this E originally in the question. Now, this now becomes E times E gives us E squared. So this becomes half KE squared. This is also work done. So we have 2 formulas for work done. Either you use F is equal to, W is equal to FE divided by 2, or you say this is equal to KE squared divided by 2. So it depends on the question. If you are given the force and the extension and you're asked to calculate the work done, you use this formula. But if you are given the force constant and the extension and you are asked to calculate the work done, you divide by 2. Also, another important thing you will not see in your textbook that I will teach you now is work done in graph. Now this is not that popular, but Jamb normally, specifically Jamb will always ask you. Now work done can mean 2 things under elastic material. Remember, the work done means energy stored. Now, when the elastic material is on its own, without any force being applied to it, the energy stored in it is a potential energy. But once it starts performing work, if you put a load, for instance, on the string, now that energy now converts to kinetic energy. So work done in an elastic material can also be written as mgh, which is potential energy, divided by, is equal to half mv squared, which is also equal to half Fe, which is also equal to half Ke squared. Now it depends on the question. All these energies are equal, so you can pick mgh is equal to half mv squared depending on the question. You can equally equate half mv squared to half Ke squared, and so on and so forth. So it depends on the question. If you are given extension, velocity, and so on, you use this. Now the last part of energy stored in an elastic material we are going to treat now is in terms of graph. This one is not all that popular, and the questions on this normally comes once in a blue moon. Now if you are plotting, okay, first of all know that energy stored in an elastic material is equal to the area under the graph. Energy stored is equal to area under the graph. Please note this, very important. Sometimes for those writing Waec, they will ask you, what is the significance of the area under the graph of an elastic material? In that case, what they are asking you is, what does it mean? What it means there is that it is the energy stored or the work done by that elastic material. That is the significance. So this part of elasticity is not that popular. So please note this. Okay, now let's see how the question appears. If in practical aspect you are plotting force against extension, anything the graph forms is what you are going to solve. Now let's say that the graph forms something of this nature. Now if the graph forms this diagram, the work done or the energy stored has a different formula. The energy stored when you are talking about graph is not constant. It depends on the shape of the graph. Now something like this, we choose this as center from here to the circumference of this curve. And we know that any line drawn from the center to any part of the circumference of a circle is a radius. Therefore, the work done in this particular graph, the work done is equal to pi r squared, which is area of this divided by 2. Please note this is very, very important. Area under the graph, when you have a semi, is pi r squared divided by 2. Now this is a separate case entirely. We have another case, let me put it down this way. We have another case where if you plot the force against the extension, you can have something of this nature. In this case now, they will ask you, what is the area on this graph? Maybe they can label it, you can just label anything they like, and they'll ask you, what is the energy stored in this particular elastic material from O to C? Or they can say from O to A. In that case, now everything changes. If it is from O to A, this is what you have. Now, from O to A forms, if you complete this, forms a right angle. So the energy or the work done by this elastic material from O to A is equal to the area of the triangle. Area of triangle. But if they ask you, what is the area, or sorry, the energy stored or work done by the elastic material from O to C? In that case now, you have to complete this way. The whole diagram now forms a trapezium. So instead of now area of a trapezium, sorry, area of a triangle, this becomes the energy is now equal to area of a trapezium. So please note this. This is actually the last part of elasticity, and it's normally not seen in textbooks. Very difficult to see in any part of textbook we are doing. So note this. Now we are going to solve questions under energy stored on this. Just one question and another one question to express how we solve question under the graph. The rest of the questions you are going to see it in your exercises, and they are past questions. You see so many questions on this. Okay, with this we come to the end of this after solving questions. So question time now. This is the question that's going to express the first part of the work done, or the energy stored in elastic material. Now the question says, find the work done when a force is applied and a string resulting in an extension of 20 meters. If the spring has a stiffness of this. Now, from the onset, I told you that stiffness is another name you call force constant. Very important. Force constant is called stiffness. Check the unit before solving. Every unit is correct. So we are looking for the work done. We have, write out the parameters, we have the extension, E, 20 meters. Now after the extension, the next thing we have is the stiffness, which is the force constant, K, 500 Newton per meter. Now the next thing, we are looking for work done. Let's call it W. Now from our equation of work done, we are told that the work done is equal to half. We cannot use Fe. Why? Because we don't have force. What we are going to use is the second formula that says Ke squared. Now when we apply this, we have half times, what is our K now? 500 over 1 times E, which is 20 meters, all squared. So we believe 2 can divide this and we have 250. Now multiplying this, squaring this, and multiply by 250. This is 250 times 400. This will give us 10,000, 100,000 joules. Depending, now if they want you to convert to kilojoule, what you do is you divide by 1,000. If you divide this by 1,000, this becomes 100 kilojoule. That is what the answer will give you, 100 kilojoules. So it depends on the question. Now, if you want more questions, go to the exercise section. So many questions on this are solved there. So many exercises, go to your past questions. You see a lot of Jamb questions on this. Questions already solved, and it will prepare you very well for your exam. Okay, let's solve one more question concerning the graph, the graphical aspect of it.